Hey, it's Theo. Some of you might know that I've been looking into lithium-ion batteries as well as energy storage for renewables. One of the problems I've faced while looking into batteries and reading research papers about complex chemical processes is that it's very hard to visualize what's going on in the reaction, what's actually happening. So, in order to visualize all my findings on lithium-ion batteries, I basically decided to make a lucid chart, a digital representation of all the processes that happen. I've divided this into 4 levels on lithium-ion batteries, going from level 1, which is the high-level explanation of how a battery works, to level 2, where we talk about different materials that are used in lithium-ion batteries, as well as the redox process. Level 3, going very deep into chemical processes that happen in a battery, as well as going deeper into the different materials, as well as the different solvents in the electrolyte. And then level 4, talking about different types of batteries, as well as voltage profiles and different battery structures for the cathodes. So hopefully you can learn a huge amount from knowing nothing about lithium-ion batteries to having an intermediate understanding of the technology.
Y'all niggas got me hot. If you know this shit, sing along. Niggas got me.
So you can basically break down a battery in 3 things: an anode, a cathode, and an electrolyte. The anode is the negative terminal, and the cathode is the positive terminal. During the discharge, the lithium atoms start here in the anode, the negative terminal. One thing you have to understand about lithium is it has 3 electrons. 2 are orbiting around its first layer, and then 1 in its outer layer. So the 1 in its outer layer is called the valence electron, and lithium really wants to get rid of its 1 valence electron. So when there's a pathway from the negative terminal to the positive terminal, the valence electrons leave and are attracted to the positive terminal. As we know in basic chemistry, when an atom is missing an electron, a valence electron, it becomes an ion. Lithium becomes an ion and wants to rejoin its valence electrons. So it goes through this thing called the electrolyte. As you can see, the lithium ions are passing through this electrolyte substance to get to the cathode. This is the inverse during the charge. Also, current collectors are just these things that collect the current. When the electrons want to leave, they get collected by the current collector, and then they pass through this circuit, which basically gives the power you need for your phone or your electric car. One of the things I have to explain is the redox reactions. Basically, in every battery, not just lithium-ion batteries, there are 2 reactions happening: reduction and oxidation. Oxidation is losing electrons, and reduction is gaining electrons. Oxidation plus reduction is called redox reactions. During the discharge, when the valence electrons are leaving the anode is getting oxidized. During the discharge, when the valence electrons go to the cathode, well, the cathode is gaining electrons, so reduction happening. Let's go a bit into the materials that compose a lithium-ion battery. So the anode is usually a crystallized graphite structure. So the lithium atoms start here, wedged in between these layers of graphite. This is called intercalation. So as we know, they go through this electrolyte, right? Well, one thing you need to know about the electrolyte is it's a non-aqueous electrolyte, meaning that lithium ions are dissolved in organic solvents, which are solvents that are carbon-based. So carbon-based solvents. What does that mean? Just solvents that have carbon atoms in them. And the cathode is usually a lithium metal oxide. So generally a combination of lithium, oxygen, and some kind of metal. There's different types of lithium-ion batteries, such as lithium iron phosphate, lithium cobalt oxide, but what you really need to retain is it's usually just these 3 things: lithium, oxygen, and some kind of metal. The current collectors are aluminum and copper, because these are very conductive materials. So now that we've explained level 2, Let's go into level 3. Okay, so there's a lot here, and so I don't want you to get overwhelmed. We'll go through this one by one. Let's talk about the anode first, then the electrolyte, the cathode, and then talk about the things I've added. The anode is not really different. I just forgot to mention that 1 lithium atom per 6 carbon atoms. So as we mentioned before, the lithium atoms are intercalated in the graphite, and so there's 1 lithium atom per 6 carbon atoms. The electrolyte is composed of 3 things: an additive, organic solvents, and lithium salts. So a lithium salt, usually lithium hexafluorophosphate, is dissolved in organic solvents such as ethylene carbonate, dimethyl carbonate, propylene carbonate, diethyl carbonate. So we already talked about the organic solvents, but let's talk about the lithium salts. So this means there are already lithium ions moving through the organic solvents, which makes the lithium ions passing through from the anode to the electrolyte go faster through the electrolyte. So let's explain what the additive does. It forms the SEI. What the SEI and the CEI for the cathode, both are different. CEI is for the cathode, it's way thinner, and the SEI is a bit thicker. Basically, there's this protective film over the cathode and over the anode that is formed when the organic solvents, the additive, reacts with the anode and the lithium ions. This protective film that extends battery life to thousands of cycles. So basically what you have to take away from the electrolyte is lithium hexafluorophosphate is dissolved in organic carbonates, and there's also an additive that forms the SEI, which is this protective film over the anode and the cathode. So let's talk about the cathode. As we talked about earlier, the cathode is usually a lithium metal oxide, and as you can see here, the cathode for the battery in our phone is cobalt, a lithium cobalt oxide, lithium, a metal, which is cobalt, and then oxygen, so making it a lithium metal oxide or lithium cobalt oxide. So as we talked about, the current collector is aluminum. We use aluminum because it's cheap, reliable, and is used for the cathode most of the time. We also use copper for the current collector because the metal does not react with the lithium. So now that we kind of understand level 3, let's go through level 4, and we'll take this step by step. So one of the things I had to go through was, what are the requirements for a good electrolyte in a lithium-ion battery? What we want from an electrolyte is to have high ionic conductivity, meaning that there's a bunch of ions flowing through at the same time. We really want that for our electrolyte. So in order to have high ionic conductivity with the electrolyte, we need to have low viscosity and high solubility. So low viscosity meaning that the lithium ions can flow through the electrolyte pretty easily, and high solubility meaning that the organic solvents can cut the ionic bonds between the lithium salts. Chain carbonates having this kind of structure, a structure of a chain. Chain carbonates include dimethyl carbonate, diethyl carbonate, methyl ethyl carbonate. And what chain carbonates offer is low viscosity, meaning that the lithium ions can flow really easily through because of the chain carbonates. But cyclic carbonates, meaning ethylene carbonate, propylene carbonate, have high solubility, which means that they can cut the ionic bonds in the lithium salts pretty easily. So as we talked about earlier, there are different types of batteries. The one I'm going to talk about first is LFP. A cathode is usually lithium metal and an oxide. So here there's lithium iron phosphate. That's for the cathode, and then for the anode it's graphite, LiC6. What you really need to retain for, on LFP is that it's an olivine structure. And so let's go through these 3 structures, and then I'll explain voltage profiles. So there are layered structures, spinel structures, and olivine structures. Olivine structures are one-dimensional, meaning there's one pathway for the lithium ions to go through. Layered structures are two-dimensional, which means there are 2 pathways for the lithium ions to go through. And spinel structures are 3-dimensional, meaning there's 3 pathways for the ions to move through. Olivine structures here are one-dimensional, which means there's one pathway for the lithium ions to go through, and that's the structure that we have for the cathode in LFP. As you can see, lithium, iron, phosphate, and then the O4. What we can basically get of that is there's one place where the lithium ions can go, which gives lithium iron phosphate a high stability. So voltage profiles are, you have the cell voltage, which right here it's 3.5 voltage usually, and then there's the normalized capacity, which is how much energy can it store, and then the volts, how much pressure is going through. So the capacity is basically measured in amp hours. If you don't know what an amp is, it's a coulomb per second. It basically measures the current. So if you can think of it as the water flowing through, and then the volts is the pressure that we put on the water or on the electrons that are flowing through our circuit. During the charge, this is a charge voltage profile. The volts go up because now it's charging, and here it has this high stability, which gives it this plateau, and then it goes up because now it's fully charged, right? That usually ends at 140 milliamp hours per gram. LFP has an olivine structure, which gives it a high stability, and its voltage is 3.5, and the normalized capacity is usually around 140 milliamp hours, depending on this. So this is a discharge profile where it's going down, and this is a charge profile where it's going up. As you can see, my graph, this is a charge profile. As we talked about, there's NMC, right? NMC is lithium, nickel, manganese, cobalt oxide. There's not really much to retain in this structure here, but what you have to understand is that for lithium, nickel, manganese, cobalt oxide, it is a layered structure, which means it doesn't have the plateau that lithium iron phosphate has, but it has a higher voltage and a higher specific capacity for milliamp hours. So what NMC gives is, since there are more pathways for the lithium ions to go through, there's more volts as well as there's more capacity for in milliamp hours. So, but there's less stability because, as you can see, it's going down really fast and then it's going up really fast. It's kind of right? As here, it's just it's a plateau. It's a straight line. So it doesn't have the stability that lithium iron phosphate has, because now it has a layered structure, and spindle structures are three-dimensional, which means they would potentially have more volts and more specific capacity, but maybe less stability when it comes to olivine structures, which are one-dimensional, less volts and less capacity, but more stable. So solid-state batteries have a solid electrolyte, that's why they call it solid-state batteries, and the anode is made out of lithium metal, so just lithium, not graphite, which means there's more energy density. If the anode is just lithium, there are more lithium ions that are going through, which means you don't need the problem that you have with graphite, where it's 6 graphite atoms per lithium. Now, before we go, let's talk about redox flow batteries. This is a different type of battery. This is used for grid storage, but I'll go through it a little bit. There's usually a positive fluid tank, electrolyte, a liquid containing a certain quantity of vanadium, so V5+. So this is a positive fluid, and then here it's V2+, which is the negative fluid. These are big tanks, and then they're pumped into these little tanks called the cell stack. They form hydrogen ions. The hydrogen ions pass through during the charge from the electrolyte positive fluid to electrolyte negative fluid, and then during the discharge they go from the electrolyte negative fluid to the electrolyte positive fluid, and there's electrons flowing through. So notice that most of these structures are actually, even like redox flow batteries, are actually just the same principle, which is ions moving through a certain substance to go to a positive or negative terminal, and also just the electrons flowing through to the circuit to power your car or anything you really want. So I hope that was useful. It might have been a bit complex. Maybe you didn't understand, or maybe you really did understand. I just hope I could take you from not knowing anything about lithium-ion batteries to knowing actually a little bit about energy storage as well as lithium-ion batteries and why they're useful.